This is the Miller's planet. It's the closest planet to the fictional black hole Gargantua. Miller's planet is part of the science fiction movie Interstellar, and it orbits close to the black hole called Gargantua. A black hole is an incredibly dense object with gravity so strong that not even light can escape its pull. So what's so special about this scene? Well, just in the span of this 5-second clip from this planet, a lot has happened on Earth. I mean, a lot. What makes Miller's planet significant is how differently time passes on it compared to Earth. On the surface, time moves much slower due to its proximity to the black hole. So, while the characters spend just a few seconds or minutes on the planet, years are passing on Earth. This concept is central to the movie and is a phenomenon called time dilation. In this video, we're going to explain time dilation while bringing the context of what happens in Interstellar. This refers to how time dilation works, both in theory and in the context of the movie. Time dilation is a concept from Einstein's theories of relativity, and it's shown dramatically in Interstellar through the different time experiences on Miller's planet and Earth. We touched upon the fundamentals of this topic from our previous video about Einstein's relativity. You can check out the video here. But just to give you a brief summary, we can say the following. To fully understand time dilation, one must first grasp Einstein's theory of relativity. The video had previously covered these concepts, but here's a simplified recap for context. The two types of time dilation. Recap of Einstein's relativity. Under the influence of a strong gravitational field, time slows down. The first type of time dilation is called gravitational time dilation. When you're near something with a lot of gravity, like a black hole, time will move slower for you compared to someone far away from that gravity. This is part of Einstein's general theory of relativity. So if you're just hanging out near a massive object, you will experience the effect of time going slower. If you were near a black hole, time for you would pass slower compared to someone far from it. You wouldn't notice anything unusual yourself, but someone watching from a distance would see you in slow motion. But gravity isn't the only thing that can warp time. According to another one of Einstein's theories, special relativity, time slows down for an object when it moves. The second type of time dilation is special relativity, which explains how time slows down for an object moving at high speeds. The faster you move, the slower time passes for you. For example, astronauts on fast-moving spaceships experience time slightly slower than people on Earth. Combining these two concepts together, we could consider this scenario. Suppose that we walked up a flight of stairs. Our body is slowly moved away from Earth, meaning that we will experience time going faster. But at the same time, since we are not stationary while going up, we should experience time going slower. This example demonstrates how both gravitational time dilation, being farther from the Earth's gravity makes time move faster, and special relativity, moving up the stairs makes time move slower, are at play simultaneously. These two effects work against each other, but are usually so small on Earth that we don't notice them. The example of two people in different gravitational fields. Let's consider two comparable cases. We have person A, floating nearby a massive object with a lot of gravity, and person B just casually floating in an empty void of space. This introduces two scenarios where person A is near a massive object, like a black hole, and person B is far away from it in a place with almost no gravity. Person A shines a green laser beam towards person B. Because light is a form of vibration, the laser beam has a color that corresponds to 600 trillion vibrations each second. Light waves have a specific frequency, measured in vibrations per second. A green laser beam vibrates 600 trillion times per second. Now, light is also a form of energy. And as that beam of light comes out of the gravity of the massive object, it loses a lot of energy. This loss means that there is a decrease in frequency. When light escapes the gravitational pull of a massive object, like a black hole, it loses energy. This causes its frequency to decrease, a process called gravitational redshift. The light shifts from a higher frequency, like green, to a lower one, like red or even radio waves. So by the time that beam of light reaches person B, its frequency will have decreased by some factor. As the light moves from the high gravity area, where person A is, to the low gravity area, where person B is, it loses energy and its frequency decreases. That means, instead of the green light at 600 trillion vibrations a second, person B gets only, let's say, 10 billion vibrations per second, which is a microwave radio beam. By the time the light reaches person B, the frequency has dropped so much that it's no longer green light. Instead, it could be something like a microwave signal. Gravitational redshift and time differences. This phenomenon is called gravitational redshift. Gravitational redshift happens when light loses energy and changes frequency due to the influence of gravity. But not so fast. Individual wiggles don't just go anywhere and disappear. Since person A creates 600 trillion wiggles every second, while person B only gets 10 billion every second, the only way this can happen is if 1 second on one astronaut's clock is not the same as 1 second on the other astronaut. The key takeaway is that the difference in light frequency can only be explained if time is passing at different rates for person A and person B. Time is not the same for both astronauts. In other words, it only takes 1 second for person A to create those 600 trillion wiggles. But it will take 60,000 seconds, or nearly a day, for person B to receive them. This means that for every second that passes for person A, it takes nearly a full day for person B to experience the same amount of time. The biological impact of time dilation. Our clocks run at widely different rates. And by clocks, I don't mean just mechanical or electronic devices, but also biological clocks like your heart, lungs, your brains, etc. This difference in time doesn't just apply to clocks, it affects all processes, including biological functions like breathing and heartbeats. If you're near a black hole, your body's functions also slow down from the perspective of someone far away. Person A takes a breath, and takes another breath and measures a few seconds between the two. For him, everything feels normal. To person A, everything seems completely normal. Time passes just like it would anywhere else. Their heart beats, they breathe, and their brain functions normally. On the other hand, person B, watching person A through a telescope, sees everything in slow motion, with several days passing between the two breaths. But person B, watching from a distance, sees person A moving in slow motion because time is passing much slower for them. What feels like seconds to person A could be days for person B. Time dilation in Interstellar. The section about Interstellar explains how time dilation is dramatized in the film, with extreme differences in the passage of time on Miller's planet compared to Earth. The filmmakers used these scientific concepts to enhance the movie's storytelling, but in reality, time dilation of such extremes would only occur near something as intense as the event horizon of a black hole, not a regular planet. Overall, this explanation shows how Einstein's theories of relativity affect time differently depending on gravity and movement. In the movie Interstellar, this concept is illustrated by the huge differences in time experienced by astronauts on Miller's planet versus people back on Earth.